So we were talking about transactions, asset properties, recall, atomicity, consistency, isolation, durability, and what is this schedule, why we need schedules, what is serial schedule, what is serializable schedule, what do you mean by equivalence of schedules, and then we were talking about conflicts and what are conflicts. So we started by looking at an example where we had a write-write conflict where one transaction overwrites the data that another transaction wrote to before it committed. There are a couple of other types of major conflicts that you can see with transaction schedules, and the next one is a write-read conflict, also called a dirty read or reading uncommitted data, and a read-write conflict, also called an unrepeatable read. So we will look at these three conflicts with more examples. So here's an example for the write-write conflict. You have a schedule with two transactions. One reads A, and then the other one starts and reads A and writes A, and then T1 writes A. So this is a conflict, a WW conflict, because T1 overwrites T2's update without reading the new value of A written by T2. So this schedule, because it has a WW conflict, is not serializable. Now, what happens if T1 is the following? You do not have a read, you just directly write A. After T2 has read and written to A, and then it commits, and then this one commits. Does this schedule have a WW conflict? Why?
Because the writing A without anything read before it indicates that it's going to overwrite the other thing no matter what.
This is going to overwrite no matter what.
Yeah.
So if it is, so you're saying it's serializable. What is it equivalent to? Is it equivalent to T1 followed by T2 or T2 followed by T1?
What's equivalent to T2 followed by T1?
Are you sure?
I think
What about this one?
read B.
If you have T2 followed by T1,
Yeah, it does.
it will not be the same. So it's still not serializable. Okay, but now since you have a transaction that doesn't read anything and just blindly writes to it, we just call it a blind write. Okay? Write-write conflicts are still possible even if you have blind writes. Okay, write-read conflict. What does that look like? Now here you have a schedule with T1 reading A, writing A, T2 reading A, writing A, reading B, writing B, committing. This one reads B, writes B, and commits. Notice that here, the writes of A and B that T1 does might be correlated in some non-trivial way. In our example, where we had to transmit some money from the checkings to the transfer some money from the checkings to the savings, the writes of A and the writes of B are related. They are not independent. Okay? And so what you might end up getting in this scenario is that T2 could actually read an inconsistent database. Recall from our example that here you might maybe do a reduction in the checking balance, and then here you probably do an increase in the savings balance. But now that T2 starts here, it starts by reading an intermediate value of A and B that is from an inconsistent intermediate value of the database. Recall that a transaction can take the database through an intermediate inconsistent state, but at the time of committing, it brings it back to a consistent state. But because this transaction reads an intermediate inconsistent database, it ends up having a write-read conflict. And that is because you have written to A, and you're reading A, and you're written to B here before you read this, before this one reads B. This schedule is not serializable because it has a write-read conflict. Does this make sense? A transaction can take a database through an inconsistent state as long as it takes it back to a consistent state. Because this other transaction now sees an inconsistent database and operates with that and then commits, it ends up leading to inconsistency in the end. Okay, what is a read-write conflict? It's also called an unrepeatable read. So here, notice that the two reads of A by T1, which is over here and over here, might actually yield different results. So notice that here I've changed the transaction, and you have different objects, so it's not the same example. T1 reads A and writes blindly to some object C, and then it reads A again and then writes blindly to some object T. Okay, so this is a different example from the previous slide. T2 comes in between, reads A, writes A, reads B, writes B, commits. So what ends up happening here is that T1 is reading some value of A here, reading another value of A here, but someone else came in between and rewrote the value of A. These two values may not be the same. And so you end up having this problem called the unrepeatable read problem. You have a read followed by a write by somebody else, and then you're doing a read again. So that's why I'm calling it an RWR conflict. For an unrepeatable read to occur, you need to have repeated reads. The book calls it RW conflict, but it doesn't make much sense if you have just R and W. So in this case, you end up reading different values of A because some other transaction came and wrote it. And therefore, this schedule is not serializable. Okay, so if you try to put T1 before T2 or T2 before T1, you might end up with you might end up with a different result than what this schedule gives you. Okay, so the schedule is not equivalent to either of those two serial schedules. Okay? Can I help you?
Sorry, I got so
Sure. Okay. Any questions about conflicts? Write, 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 read, and read, write, read. Okay, so these conflicts characterize the kinds of schedules, issues with schedules that make them not serializable. So here's a review question. Here's your schedule. Is this serializable? Read, write, read, read, write B, write A, read B, write B. This one commits, this one commits. Take a moment to think about it. See if it is serializable. If so, you have to tell me what is it equivalent to. T followed by T1, sorry, T1 followed by T2 or T2 followed by T1? Yep, this is equivalent to T2 followed by T1. But does it have any conflicts? Does it have a write-write conflict? Are you overwriting uncommitted data?
Yes.
On the record B? What about the record A? And A. Oh, sorry. So you are overwriting uncommitted data. So there is a conflict, but the schedule is still serializable. Okay, so there is something amiss here. We looked at conflicts that can arise in a non-serializable schedule, but then here, this schedule is actually serializable, but it still has conflicts. Okay, so it has to do with when you're committing the transactions. If the transaction is running, and then this transaction starts, and then suppose this transaction gets aborted, then you end up in deep shit. So what can you end up with? So let's talk about aborted transactions. Notice that serializability only talks about committed transactions, and it pretends as if aborted transactions do not even exist. They did not even happen. And that's an illusion. That's an illusion created by the transaction manager, and it is only possible if we deal with two new issues caused by aborted transaction, and the first one is undoing the effects of an aborted transaction. All changes made by an aborted transaction have to be undone. Okay, recall in that example, it was serializable because both transactions were committing. If one of the transactions was aborting, then you end up in an inconsistent state. So here, in order to ensure that if you have transactions that are aborting, you need to make sure that all its changes are undone. This is done using the technique of logging and recovery, and we'll talk about that in a short while. Now, there's another issue. What if a transaction that got aborted did something to the database that affected some other transaction? So in that case, you have to undo the effect of that transaction which depended on the aborted transaction's changes. That is the problem of cascading aborts. So here is an example. T1 reads A, writes A, T2 reads A, writes A, T1 aborts, but then T2 is allowed to commit. Why is this a problem? Notice that abort, yeah, well, yeah.
No, go ahead.
Here, because you're aborting T1, the changes made by T1, which includes the change to the value of A, has affected T2 because T2 is reading the value of A written to by T1. Therefore, T2 should also be aborted. However, we have allowed T2 to commit. If we do not allow it to commit, then the transaction manager, upon this abort, will automatically replace this commit with an abort. And that is how it manages this particular transaction as and when it's executing. Yeah?
So it's not able to like roll back the changes from T1 and then use the non-affected values for T2 and then commit T2?
Well, in this example, you have only two. You might have more transactions. So you'll have to worry about the interactions between all of them.
Always like if it affects another transaction, just aborts that.
Yep. So this is called cascading aborts because now T1's abort causes T2 to abort, and that could cause another transaction to abort.
And there's no more intelligent way of doing it?
Yes, there is, but typically they are too complicated to implement in practice. Okay? So let's not get into too much details about recovery, but for now, this is the problem of cascading aborts. You cannot allow a transaction that depended on an aborted transaction's value to commit because that could end up to an inconsistent state. So what about this scenario? Read A, write A, read A, write A, and then this one is allowed to commit first before this one tells the transaction manager that it wants to abort. Previously, the transaction manager saw that this one is aborting, and it replaced this commit with an abort, and everything was fine because both transactions were undone. But now, this transaction has committed. Commit means your effects are durable, asset properties. What can you do? You're out of luck. This is known as an unrecoverable schedule because the effects of the aborted transactions cannot be undone in entirety. And what is a recoverable schedule? A recoverable schedule is one in which all transactions commit, if at all they commit, only after all others that supply dirty data to that transaction commit or abort before it. Okay, so this one is not a recoverable schedule because this transaction is allowed to commit even though this transaction T1 that supplied dirty data, in this particular case, the object A, it did not commit or abort. Okay, so this one is not a recoverable schedule, but the previous example is a recoverable schedule because here, this transaction aborted before this transaction committed. Okay, so that's known as a recoverable schedule. Yes?
It seems like for this case here, this is at the application level something that you could have prevented. Like if you care about doing these in this sequential ordering,
Mm-hmm.
you could have like encapsulated the whole thing in one transaction and then, so T2 and T1 become just one big transaction and then you abort, right?
Right.
So this seems like
Yes, so that again goes back to the question of what is the abstraction of a transaction. You could have two concurrent users issuing requests to the database, and so the application will have no way of figuring out that they should belong to the same transaction. So it increases the complexity of the application. Okay, so that's why the contract between the application and the database system is that a transaction is an atomic, indivisible unit of work that has isolation and all of that. Okay, so this is a problem really with the transaction manager scheduling. Because from the application perspective, these two are isolated. From the transaction manager's perspective, because you want efficiency, you're interleaving them. But by interleaving them, you run into all sorts of trouble. Okay, and this is one of those troubles, unrecoverability. Okay? Okay, so how do we avoid this problem of avoiding cascading aborts? Well, you create a kind of schedule that is called an ACA schedule. That's not the Affordable Care Act. It's the Avoiding Cascading Aborts schedule. No transaction is allowed to read dirty data, which means it can only read the changes of committed transactions. Now that seems like a very strong condition, but it is a sufficient condition that guarantees that the cascading aborts problem will not arise. Therefore, it will also guarantee that the schedule you're getting is a recoverable schedule. Okay, so this is a sufficient condition, not necessary. You could have schedules that are not ACA but still recoverable, but if you have an ACA schedule, then it is always recoverable. Okay? So essentially, transactions read changes of committed transactions only. Now, a similar issue happens if you allow transactions to overwrite dirty data. So a transaction reads dirty data that was dirtied by another transaction, and then it overwrites it. In that case, you have to handle this with concurrency control, and I will try to get to it, but I don't think I'll have time to get to it in detail. We'll talk about it later today or in the next class about what concurrency control does when you have multiple transactions writing to the same data. Okay, so let's look at the idea of concurrency control today. Typically, in almost all DBMSs, it's handled via this abstraction called a lock. And if you've taken an operating systems course, a lock is essentially a small bookkeeping object that tells you who owns a particular object and who can write to it, who can read from it, and so on. And so as part of transaction management, the DBMS also has, along with the transaction manager, a lock manager. So what does the lock manager contain? It contains this metadata called the lock that tells you which transaction is accessing which data object. And the data object could be a tuple, it could be an attribute, it could be a cell in the table, it could be an entire table, an index, and so on. So for simplicity, let's just assume that a lock is a 3-tuple, which contains the transaction ID, the record ID, so we are only allowing tuple level, and then what is called a mode. The mode tells you whether the transaction is reading that particular object in a shared mode or exclusive mode. So what is this shared mode and exclusive mode, and what is the motivation for this? If you have multiple transactions accessing the same object, you cannot allow them to write to the same object simultaneously. But if you have both of them reading the same object, you can allow both of them to read the same object concurrently. Okay, so that's called the compatibility matrix of the modes. If you have a transaction that acquires a lock on a tuple in shared mode, it is compatible with another transaction that acquires the lock in shared mode. They are both reading the object simultaneously. But if you have an exclusive lock on a particular object, it is not compatible with a shared lock or an exclusive lock. If a transaction acquires exclusive lock, it means it could potentially overwrite the value of that object, and therefore it is not compatible with another transaction that wants to read or write that object. Okay? Any questions? Yes?
So the dash dash column, this is any transaction that does not want any lock, right?
This thing?
Yeah.
Yes, so that's basically something that's not even asking for a shared lock or an exclusive lock.
So what if it's doing writes while somebody has an exclusive lock?
Yes, so the semantics of the transaction that's performing writes is that it should require an exclusive lock.
Okay, and then in the tuple where you say it's an attribute in a table, that
Mhm.
makes sense to me, but when you say it's a record ID, that makes less sense to me.
So the record ID is essentially the metadata to tell you that you're storing a lock for the whole tuple. If you're storing a lock for the whole table, then you will store the table identifier. Okay, so this is basically an identifier for what object you're locking. And here the record ID says that you're locking a particular tuple in a particular table. Okay, so there are various hierarchies of locks. I'll talk about it briefly in a short while. Okay, so when does a transaction acquire locks for the objects that it accesses? Well, it happens during the request to the buffer manager. So recall when we talked about buffer management, there's page requests that are placed to the buffer manager, and the buffer manager knows what records are there in the buffer pool, and that's when you actually acquire the locks for that particular object. Now there's a question. I mentioned the exclusive lock is not compatible with the shared or the exclusive lock, then what happens to a transaction that requests an exclusive lock on something that is already exclusively locked by somebody else? Well, that transaction is forced to wait on a wait queue before it can access the page that is present in the buffer pool. Okay, so transactions are made to wait. They are processes, and the processes are put in a wait queue. And once the transaction that held the exclusive lock finishes, commits, or aborts, and the lock is released, this lock will be handed to this transaction that was waiting. Yeah?
What's the point of the shared lock?
Okay, if you have two transactions that are read-only, then you can do concurrent access. You can allow both of them to basically read that particular value. And so you can have higher throughput.
Why do you need a lock at all in that case?
Well, in this particular case, in this example, it's probably not needed. You could just say it's the same as not having a lock at all. But in practice, you have hierarchies of locks. And so the semantics of the shared lock become more complicated. Yeah?
I'm having trouble understanding how the exclusive mode is compatible with the default no lock mode.
It depends. I mean, in this particular case, you're saying there is no access going on that particular object. It's not going to change anything in the database. It's just doing some reads. So the semantics of this basically means you're not making any change to the database.
So, okay, so if a transaction holds an exclusive lock, something else that's like not the transaction can still read the data?
It could be a transaction, but it's reading some other object. So it could be, for example, you're reading X, reading an object A, and then someone else holds a particular lock on A for exclusive mode. This transaction that is reading A doesn't make any changes to the database, in which case it can never cause inconsistency. It's maybe just a print command that just reads the value and prints it. So you might end up getting some value that's inconsistent for the reader, for a person looking at the data, but it does not affect the consistency of the data.
So you allow it, but it's bad?
It could be bad.
Okay.
So you allow this execution mode where you do not request a shared lock, but then you'll have to be content with getting data that may not be actually real. The shared mode forces you to wait for a particular shared lock, and that will guarantee that the value that you're getting is actually consistent. Okay, so these levels will be beneficial depending on the semantics of the application and what exactly you're doing with the queries. You could always have transactions that do not update anything in the database, but just read a particular value. Okay, so in contrast here with the shared mode, you could have a transaction that's reading some object and then writing some object, and then reading some object and then writing some object. So you could request exclusive mode on one object, but shared mode on another object. Okay, so you could mix and match these different modes of operation for different objects in your transaction.
So what you were saying for like the default no lock mode, it's like if some transaction holds an exclusive lock on that, and then this other one that has no lock reads it,
Yep.
it can't rely on that data because the transaction may roll back
Yes.
or something.
Yep. But the transaction that is in this mode doesn't do any changes to the database. So it's probably just reading a value and printing it. It cannot cause any inconsistency to the database. But if you have a transaction that reads some value and then updates some other value, and they are correlated, then you better request a shared lock, because that will lead to inconsistencies in the database. Okay? Any questions? Yeah.
So when you say during the request buffer manager, so that means we should have implemented the lock in our project like it. Should we just make
Good idea. Maybe I should do it for the next year's version of this course. Ask them to implement lock compatibility. No, you don't have to worry about this, because in the project you only had buffer management for read-only queries. I didn't ask you to do any writes.
Because honestly, we have one time here OS class that's doing the buffer
Uh-huh.
the lock.
With the lock.
Yeah.
Oh, really? So you have a programming project.
Yeah, right.
Interesting.
Yeah, we've implemented this.
You've implemented this. With how many lock modes?
Quite a few. Just like one, right? It was just binary. Yeah, just locked.
Just locked or not? Okay. Well, real-world DBMSs have about 4 dozen lock modes. This compatibility matrix is about something like 50 times 50.
We consider like a semaphore or something where we allow a certain number of
No, I'm talking about the granularity of the lock. Tuple, attribute, column, there's predicate, there's table, there's index. There's so many kinds of objects in a database system, and the compatibility of shared and exclusive for different kinds of objects differs. So Microsoft SQL Server, for example, I think this data is public. They probably have something like 44, 50 something on this and on this. So some developer in Microsoft has sat through compatibility for 40 times 40 and implemented this on top of their engine.
So added granularity allows the scheduler
Mm-hmm.
to be way smarter.
Exactly.
Right?
The more granular your locks, the more concurrency you can allow. Okay, if I don't allow tuple locks, if I say you have to lock down the whole table just for updating one tuple, then you allow very poor concurrency. Okay, so what is the locking protocol? Essentially, it tells you when a transaction can acquire and release locks. I mentioned that you access the locks when you're doing the buffer management requests, but at a conceptual level, the protocol tells you when and in what order you actually have to acquire the locks. So there's something called strict two-phase locking, and strict 2PL is a protocol that asks you to basically acquire all shared locks before the read on that item, an exclusive lock before the write on that item. However, you have to retain all the locks you obtained all the way till the end of the transaction, which means either you commit or abort. Okay, so that's called strict 2PL. You request a shared lock when you want to read any particular item. You request an exclusive lock on that item if you want to write that item. But you hold all your locks till the end. There's a different version called the non-strict or just 2PL, two-phase locking. Here, you enforce number one, but you do not enforce number two. You basically say you release the lock as soon as it is not needed. So you've done a read, and then you can release your shared lock. You've done the write, then you can release the exclusive lock. Okay, so that is called non-strict or just regular 2PL.
Can you read line 1 there aloud? Like, how do you read that statement?
Request shared lock before read on item. Request exclusive lock before write on item. Okay? Yeah.
So why do you care about strict? Like, sure, you're going to acquire the lock to do some write or something. So
I'll explain now. You guys keep doing this. You shouldn't. Just wait till I finish the slide. So what happens with non-strict 2PL? This is basically a lock acquisition chart. As the transaction proceeds, time is on the x-axis. The number of locks held by the transaction is on the y-axis. There is this growing phase where you request your shared lock when you read something, you request your exclusive lock when you write something, and then at some point you hit the peak, and that's called the lock point. You're holding a maximum number of locks, and at some point you'll keep releasing locks, and then that's called the shrinking phase. This is for a 2PL. For a strict 2PL, you hold on to all the locks, and then you wait till the end, and then you suddenly release all the locks at once. Okay, so that's the difference between how 2PL works and strict 2PL works. Now, here's the thing. Both of these protocols guarantee serializability of a schedule. As long as transactions that are interleaved in a schedule follow 2PL, that schedule is guaranteed to be serializable. However, there is also recoverability. We talked about avoiding cascading aborts and recoverable schedule. Serializability only tells you you can guarantee atomicity, consistency, and isolation. Recoverability guarantees durability. Because if a schedule is not recoverable, then you are out of luck. You either end up with inconsistent data, or you have to violate durability. So if you want all of ACID to be enforced, which is what you ideally want for a consistent database with high performance and so on, you want recoverability as well. And strict 2PL guarantees avoiding cascading abort schedules and thus recoverable schedules on top of serializable schedules. And the intuition is clear, right? Because non-strict 2PL, you can release locks in between the transaction. Now somebody else can acquire a lock on that object in between and then do changes to it. And so you might end up with some messy situation. Strict 2PL, you hoard all the locks till the very end. Anybody else that tries to come in and acquire a lock will be forced to wait till the very end. Yes.
So that was like that one slide where it wasn't the cascading of work, it was like the commit that happened before the other commit. That would just cause that transaction to sleep on.
Yep, exactly. And that's what I'm going to show next. Now notice that all of this releasing of locks and stuff is not done by the application or the transactions. It's done by the DBMS lock manager working in tandem with the transaction manager. Okay, so it's all taken care of under the covers transparently. The user and the application doesn't need to worry about it. Again, one of the benefits of declarativity. Okay, so here's an example. You have a transaction, reads A, writes A. This one reads A, writes A, reads B, writes B, commits. Reads B, writes B, commits. Is this schedule serializable? How many of you think this schedule is serializable? How many of you think this schedule is not serializable? Are there conflicts? So, if it is serializable, what is it equivalent to? Which serial schedule? T2 followed by T1? Here, T2 is reading the A written to by T1. So it cannot be equivalent to T2 followed by T1.
The other one.
Okay, T1 followed by T2. T1 followed by T2. Okay. T1 is reading the B written to by T2. So it cannot be equivalent to T1 followed by T2. So it's not serializable. Exactly. Is it recoverable? Not necessarily. It's not recoverable because you're allowing T2 to read dirty data from T1 even though T1 has not committed. Okay, so recoverability means a transaction basically reads only data, dirty data from committed transactions. Now what happens when you enforce strict 2PL and then what happens to the schedule? Well, the first thing is the DBMS will force T1 to obtain a shared lock on A before reading A, an exclusive lock on A, so that's called lock escalation. You had a shared lock, now you're escalating it to an exclusive lock because you want to write A. And now, because you're following strict 2PL, T1 is going to hold the lock, exclusive lock on A, and when T2 comes in and tries to do read A, T2 will be forced to wait, and therefore it will be forced to wait all through the end of T1. Okay, that's your lock compatibility. Exclusive lock is not compatible with reading or writing. Now, when will T1 release its exclusive lock on A? Exactly. Only after committing, you do an unlock on the exclusive lock on A. And now T2 can resume by doing a shared lock on A. And so basically what you end up with is a schedule that's serializable. In this particular example, it's actually all of T1 executes first and then all of T2 executes. But in general, when you have a lot more data objects, you could still have interleaving, except it will not be as much as without strict 2PL. Okay, so you can still have interleaving when you have multiple objects and have some concurrency, but it's in some middle point between having fully serial executions and arbitrarily scheduled executions. Now, homework, what happens if we use non-strict 2PL? Okay, given the schedule that was originally listed, go back, think about what if you use non-strict 2PL, how will the schedule get modified? Excuse me.
So
Yeah.
is it correct to think about this as the scheduler tries to do interleaving
Mm-hmm.
best, like using whatever heuristics to the best of its abilities, irrespective of the locking paradigm, and then it superimposes the locking paradigm, right? Because I would have said that it makes no sense to even interleave this. Clearly, you're doing T1 and then you're doing T2.
Right.
In this case.
Right.
So why would the scheduler even offer this?
Suppose you have T2, before it is reading A, say it reads D and then writes D. Then you can have concurrency. T2 will not be forced to wait till here. It could actually read D and write D here. Okay? So there's no conflict there. There's no conflict in terms of the locks. Even though it has an exclusive lock on A, it doesn't have any lock on D. So T2 can still acquire the exclusive lock on D and proceed concurrently.
That makes sense, but does the scheduler try to interleave irrespective of the locking paradigm?
Nope, they both work together.
Okay.
Yeah.
So if we get a question something like, are these two transactions serializable or recoverable or something like that,
Mm-hmm.
we don't really know. We don't have enough information until we know the locking.
You need to know the locking protocol.
Protocol.
Yep, you need to know the locking protocol. Well, if you're given a schedule without the locking protocol being specified, then you will have to assume something, and you'll have to justify your assumption.
Okay.
Okay?
So it seems like it'll never be the case that something is not serializable and then adding one of the. Wait, no, never mind.
Yes.
Won't there be a deadlock if, like, for example, T1 is doing A, B, and T2 is doing B, A? Never mind.
You guys keep doing this. Yes.
I have a question on the previous slide.
Yeah.
So the reason why you said that T1 and T2 are not serializable is because T1 tries to read B, and B depends on B and T2. But if we say, oh, locking, we just do T1 first, T2 first,
Mm-hmm.
isn't the B value T1's reading different than the values that is proposed by that schedule?
Yes. So when we talked about serializability, a schedule that is equivalent to some serial schedule is allowed to be correct. Okay, so it doesn't matter what the value of T1, what the value of B T1 reads is, as long as you're reading either everything that T2 finishes and then you do T1, or T1 runs first and then T2 runs next. Okay, so that's the semantics of the application, which gives you these two transactions concurrently. It is okay with either of them executing in any order. So as long as your schedule is equivalent to some serial schedule, it is said to be serializable. Okay, so think about like your Amazon, and then you have 100 people trying to buy one item, which is they have only one in stock. They don't really care who buys it. Somebody has to buy it. They cannot sell it to two people at once. They have to sell it to exactly one person.
So the situation he just described seems to me that when you do care what value B is reading is dependent upon T1 or whatever, this is when you need to make these all one transaction.
Or the application withholds T2 and then runs T1 first. It doesn't issue the transactions simultaneously. Okay? Okay, great. So let's look at deadlocks. What is a deadlock? You guys must have studied this in your OS course. When two transactions end up waiting on each other. So here's an example. T1 acquires an exclusive lock on B, and then T2 acquires an exclusive lock on A. And then T1 requests a shared lock on A, and T2 requests a shared lock on B. But because T1 requests a shared lock on A and T2 holds an exclusive lock on A, T1 is forced to wait. And now T2 is executing, and it requests a shared lock on B, but unfortunately T1 holds the exclusive lock on B, so T2 is also forced to wait. Neither of them will make progress. You end up with a deadlock. Okay? Now, does this schedule satisfy 2PL? And does it satisfy strict 2PL? Yes. The transactions are acquiring locks as and when they need them. Nobody has released their locks. Everybody holds their locks. So it satisfies strict 2PL, not just non-strict 2PL. So even with strict 2PL, even though you have serializability, even though you have recoverability, you could end up with more trouble, and that's deadlocks. And typically the way this is handled is, as you know in your OS course, deadlock prevention. You try to avoid schedules that could cause deadlocks by heuristically determining based on what is called the conflict graph during the schedule formation, and try to avoid cycles in that conflict graph. Or you could do deadlock detection and breaking. When you have transactions that are not making progress, the transaction manager has timeouts, and it tries to basically abort transactions depending on the timeouts. And again, these are parameters that a DBA sets. Okay? There are other solutions. We will not go into details about deadlocks.
Is non-strict 2PL less likely? Because it's going to try to release them as soon as possible?
You mean deadlocks with non-strict 2PL?
Mm-hmm.
So here the deadlock is happening during the lock acquisition phase. It doesn't matter whether it's non-strict or strict. Okay?
But
But
like if you were to say like true or false, you should would it be reasonable to expect less dead logs to occur under 2PL versus 2PL?
it depends. It depends on how many transactions there are, what objects they are accessing, and so on, when they come in, and so on. Okay? Okay, great. So I mentioned granularity of locks. There's different granularities. You could have lock on an entire tuple, on an entire attribute, on a particular cell value inside a particular tuple, whole table, whole index, and so on. Typically, DBMSs do not allow you to do individual cell values. They either ask you to do a record level lock, a tuple, or an attribute level, or a table level, or an index level. Notice that it matters for your efficiency. That's the throughput. How many transactions can you handle concurrently per second? And for correctness. Because if you take an exclusive lock on tuples alone and someone else takes a shared lock on the table, then you might end up with troubles. So in this particular example, you have an update query. So it's a write operation. And you want to set the grade for a particular student. If you lock down the whole table, you're going to avoid a lot of other transactions that are probably updating some other student's records. So then that leads to poor efficiency, poor throughput. Okay? And if you request too many exclusive locks and too many transactions are requesting exclusive locks on a particular item, so in this case, say maybe the student, then all those transactions will be forced to wait back to back. And again, this is not a deadlock situation. This is a situation that's called thrashing, because there's concurrent access to the same object by multiple people, and that could cause the throughput of the system to go down. Yeah?
Is one valid granularity level to group both the relation and the index? Let's say that you're inserting into a table that has an index, and you want to simultaneously know that you can update both the index and that relation. Is there like a lock that will cover that case?
Yes, there are different kinds of locks. That's what I said there are 4 dozens. And the compatibility of those different kinds of locks differs. With an index, it again depends on, are you doing alt record, alt RID? Is the index key the same as the value that is getting attribute that is getting updated? That matters too. So there's a lot of changes. Yep.
All this granularity and the locking, um, do these implementations basically give the application developer access to all of this stuff, just the ability to perform all this granular locking, or does the implementation of the RDBMS itself implement a bunch of this and then just give the application developer some access to some of this locking stuff?
The application does not have to worry about the granularity of the locks.
Okay,
They just worry about giving the transaction to the DBMS. It's the transaction manager and the lock manager's job to figure this out. Okay, there are ways to avoid thrashing. You typically want to lock the smallest granularity. So in this case, you want to lock only the record for this particular student. And you want to reduce the time the transaction holds the lock. So there is this notion of a predicate lock, and this is again tricky. Instead of doing a tuple level or a table level, this is an intermediate point. Again, it's a trade-off between throughput and correctness. However, with predicate locks, very bizarre issues can occur. So here's an example. A predicate lock basically tells you, lock all the records in a table that satisfy some particular predicate. Like lock all the records of students of age 25. Now here, suppose T1 holds a shared lock on the table, but an exclusive lock on a particular predicate in the table. It reads the table, it updates the tuples matching the predicate because it has an exclusive lock on that predicate. Now suppose T2 is another transaction that comes in and executes concurrently, and it inserts a new table that satisfies the predicate. Okay, so this T1 held a lock on the tuples in the table that satisfy the predicate. T2 adds an entirely new tuple that satisfies the same predicate. Now if T1 reads the predicate again, it will see this new tuple that it did not see before. This is called the phantom problem. Okay, so the phantom problem can arise when you have predicate logs and you interleave transactions with different granularities of logs. And there are ways to detect and handle these issues. We will not get into details.